In this video, we are going to do a short review of lecture topics covered as the first part of Chapter 7 notes. So let's just jump right in. Let's just remember, Chapter 7 is basically titled Quantum Models of Atoms. We're really going to be focusing on this part, particles and waves, how atoms behave, as both of those with specific respect to light. We're going to go over actually a couple of variables. Okay, we have two that we're actually going to highlight at the moment, and then we're going to do one constant. Variables, first off, is lambda. Okay, this lambda stands for wavelength. And I know you're saying, Ethan, what the nuts is a wavelength? And I'm like, well, I'll tell you. I know we went off the scale a little bit, but it happens. One wavelength is the distance from a peak to a peak, or a trough to a trough of a wave. So that's what we define as lambda. The next variable is nu, which is basically a classy v, which that looks like a u. Right? And this is the frequency, which is the amount of times that any point on that wave passes a particular location on the graph. Let's say it's this. You know, how many times, or how quickly does the wave pass that specific point? That specific point. And actually, this is another way of basically saying the velocity of the wave, which is why it kind of looks like a V. You know, it makes kind of some sense when you get in there. Okay, a constant we're going to look at actually we're going to go two constants. Okay, first we have c, which is the speed of light, which is 3.00 times 10 to the 8th. That doesn't look like an 8. 8 meters per second. Okay? Notice that this is meters, where you usually get your frequencies, speeds, or wavelengths, expressions in nanometers, right? Where we remember that 1 nanometer equals 1.0 times 10 to the negative 9th meters, right? And that's something that you saw in your midterm exam that I hope you remember from there. Right? So remember that we are converting if we use the speed of light. Other constant is actually h, lowercase letter h, and this is called Planck's constant. Which equals, right, 6.63 times 10 to the negative 34 joules times seconds. And that fits in with his equation that we'll be getting to in just a moment. So, an equation, we're going to go with equations. What just happened here? My apologies. Equations. Okay, where do we go with equations? And we're actually going to have two that we look at now, and then I'm going to show you all the spectrum, the electromagnetic spectrum, and then we're going to call that a day with nodes. And just this review video in general. Okay, just this review video in general. So, actually, here we go. C, speed of light, equals, right, lambda nu, right? C equals lambda nu, and you can rearrange to solve for any variable. Okay. The next one, right, is actually the one using Planck's constant, where we find the energy. Okay, E, you'll remember, is energy. We've seen that before, so I didn't put it on our variables list, right? Equals H, our Planck's constant, nu, right? Where nu, again, is our frequency. This also can be rearranged to solve for any variable, and we will be doing that during this class. Okay. So, let's quickly touch on the electromagnetic spectrum, and then we're going to call this a day. I'm going to draw down the bottom of the page here just a wave that quickly changes frequency. Okay, I may have gone too small too fast, but whatever, it works for me. Okay. Now, what we're going to do with this actually is we're going to draw in very quickly our electromagnetic spectrum. Now, I'm going to move this up just a tad so we can write a couple things down. On this side, right, on this side, we have a shorter wavelength, right, which means a higher frequency and a higher energy. Okay. On this side, we have a longer wavelength, which actually leads to a lower frequency and a lower energy. I didn't mean to do that. Lower energy. Okay. So we're just going to draw in very, very quickly what's going on. First, at our low frequency, low energy, long wavelength, we have radio waves. Yeah, I know what you're thinking. Radio Gaga. Okay, it's a Queen song. I'm just kidding. It was part of trivia the other day. Moving on. Anyway, I just want to move that up just a tad. Radio. Okay. Radio waves, they're very long. They travel very far distances, as do radio waves in terms of playing the radio, in terms of on your car and stuff like that. AM waves are super, super long. So, anyway, next, microwaves. Great for popcorn, Chinese food leftovers, pizza, also knowing that they have longer wavelengths, lower frequencies, and lower energy than, and here's a common misconception. Everyone thinks it's infrared, okay? This spelling is wrong. Don't humiliate infrared. Be nice to it, okay? It is infrared. Infrared, okay? Infrared. That's actually how night vision cameras and stuff like that work. So very, very cool. I'm going to write viz and extend this. It doesn't really go into infrared, but this is how I'm just going to write it, so sorry. Next, in terms of going up in frequency and energy, we have UV light. Those actually both look like U's. So we're just going to redo that real quick. UV light. Okay. There's actually two types of UV light. There's UVA and UVB. UVA is actually something that's much harder to block against, since it's actually what causes aging and sunspots and all that stuff. And chemical sunscreens with chemical filters such as avobenzone don't necessarily filter out UVA rays. They're very good at filtering out UVB by creating a film on your skin. But UVA rays really, really need a physical sunscreen such as a zinc or titanium dioxide-based sunscreen to filter those out. Next on up the list, we have X-rays. These are used to see your bones and be super cool in hospitals, and these can do this because of their high frequency and high energy, as they can transmit things. More or less, they just have the ability to permeate the physical confines of the skin and basically opaque surfaces of the body. So how cool? How cool. Last one is gamma. I don't really know if you guys know the symbol for gamma, so I'm going to write out gamma and do the symbol. Okay. Gamma rays are like super, 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 super duper high frequency, and they're V scary. So, moving on. Not actually scary, and you'll actually see that kind of stuff in physics if you continue down that path. Really quickly, we're just going to just write in our Roygbiv in the visible spectrum. And I know there might be a lot of willingness to write Roygbiv, but I'm here to tell you that is wrong. Okay, the way we do this is red always goes the closest to infrared. Okay? And then we write Roygbiv. Oh, I forgot the B. Oh, boy. Backwards. Okay? Since violet is then the closest to ultraviolet. Okay, so that's how we remember that there. If you have any questions, please don't hesitate to email me or let me know. I hope this video helped, just as being a really short 10-minute review. I tried to keep it shorter, but I just want to do a little more explaining. But anyway, if you have anything to let me know, please do. And thanks for putting up with me as I learn this new software along with you guys. So thank you so much, and I will see you later.